Okay, so I start lecture. Okay, so start with where we left last time. So let me make some connection with what Professor Mukunda was saying about phase space. And so if you remember, I had defined a dynamical system as a system comprising n dynamical variables x1, x2, x3 up to x small n. So for a Hamiltonian system, indeed, as Professor Mukunda mentioned, so this n is going to be equal to 2n, right, where n is the number of degrees of freedom. So half of these variables would be the generalized coordinates, and the remaining half will be the generalized momenta. Okay. So we will come to Hamiltonian system in more detail, hopefully tomorrow. So this is just to say that, that's why I am using this small n to denote the dynamical variables. And for a Hamiltonian system, which is a conservative system, we will see that it indeed satisfies divergence of f equal to 0 identically. At every phase space point, divergence of f equal to 0. It's just a consequence of the equations of motion. Okay, so let's stick with that previous notation. And yesterday there was another confusion regarding this trajectories, whether they can self-intersect and so on. So let me introduce, I should have talked about it yesterday, but I somehow forgot. Introduce this notion of vector field. This is something that is used. So if you remember this, so this set characterizes the dynamical system. Completely characterizes the dynamical system, and as we mentioned, we have this n-dimensional phase space x1 whose axes are x1, x2, x3, x4, and dot 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 and so on up to xn, where the state of the system is represented by a single point in that phase space. And if you recall the equations of motion that I had put in this vector notation, x dot is equal to f of x, where if you remember, this x is an n-dimensional column vector, and so is f. Okay. So if you look at this equation, you immediately realize that what f is giving you is, it is giving you the velocity, the local velocity in this n-dimensional space at the point x. Think of it in, suppose n is equal to 1. Okay. So then what is it saying? It is just saying that x dot is equal to f of x. So f of x is really telling you the velocity at point x. Okay. So if you think of it in this n-dimensional space, so what this f of x is giving you is, it is giving you a vector which is defined at every location. Okay. And your actual phase space trajectory will be such that the tangent to it at every point, you remember that the tangent of a curve at every point is the direction, and is the direction of the local velocity. So it's like that in this n-dimensional space, your actual trajectory is such that if I draw the tangent at every point, if I draw the tangent this way, so the tangent is really given by, suppose this is my point x, so the tangent at that point is f of x. So this is local velocity, and since this f of x is defined at every x, it is defined at every x. It could happen that at some x's f of x is 0, but it is defined there. We will see the consequence of the consequence if it so happens that if it is 0 at some points, but this function is well defined at each and every x. If I take an x and I can if I define an arbitrarily closed neighborhood of it, this function is defined there. There is no point in that. So it's called a vector field because it's a vector. That is why it is called a vector field, because it's a vector that is defined at each and every x. It's like what you see in a field, that there is a blade of grass at each and every point. So the function is, this vector is also defined at every point. So it's called a vector field. And just to tell you once more, your actual phase space trajectory will be such that the local tangent at every point is given by this vector field. Okay, so this is something that, and so now this question doesn't arise whether the So one of you had a confusion, I don't see him here probably, why the trajectories cannot, probably you had this confusion? No, he's missing, okay. Why the trajectories cannot self intersect, and I somehow felt that what he was thinking was that it could be that the particles are at the same location, but they have different velocities or something. So, in this way of thinking about it, you see that the vector is well defined at every point. It cannot be that at one point there is one vector going this way and one vector going that way, because the function is single valued. At every x there is just one f of x. It cannot happen that. So, that is why this kind of thing cannot happen, because at this point if I, there is one vector pointing this way, one vector pointing that way, that cannot happen simply. Okay, it's just okay. So, let me now come to this point of solvability and integrability, what I was planning to cover yesterday and I could not. So, that is this thing. So, let us come back to this equation. Let me also look at my notes. And what I had said yesterday is that if you give me the initial condition, one phase space point, since these are first order differential equations, given this initial point, I should be able to tell you where the system is going to be, what is the fate of the representative point at some arbitrary t, okay, because that is just a property of the first order differential equation. So, let us do the following. Suppose I ask the following question, that I start at this point x of 0. I will not draw those n axis like anymore, but so whenever I put a bar, it is a vector, okay, it is an n dimensional vector. N could be 1, 2, 3, whatever you want, whatever is the dimension of your dynamical system. So, you may ask, what is going to happen, where is this phase space going to go at a little time later, at a delta t time later. So, I ask what is x of delta t. I started off with, so this is the time, okay. So, x of t if you want. Okay, so this, if I choose delta t small enough, I can always do a Taylor expansion. So, what I will do is that I will say that x of delta t is just x of 0 plus f of x of 0. So, this is the, the tangent at x0, at times, at time 0, delta t plus higher order terms. And by taking delta t sufficiently small enough, I can take delta t sufficiently small enough that I can neglect the higher order terms. I can always do that. So, what this tells me is that given one point, I should be able to build the whole trajectory, at least numerically. Let us say on computer, what I can do is that I can choose delta t small enough, and starting from this point I go to a nearby point and a nearby point and a nearby point and so on, and if I just connect those points, I get the trajectory, okay. And this I can do for arbitrarily. Suppose I want where is the phase space point after 2 hours, I can continue this procedure. I can do it on the computer. I can run a loop, and this will tell me where the particle is going to be at some point. So,
you are due to x dot or x?
Sorry?
You are due to x dot or x?
X. I am looking, so there is no x dot, right? So, my dynamical variables are x. X dot is telling me how x is evolving as a function of time. My dynamical variables are x1, x2, x3, xn. I want to know, given the set of values at time 0, what is going to be the values at a later time. So, what I need to do is, it's just a simple thing, that if you have x dot is equal to dx dt. So, what you do is that x of t plus dt, let me not call it dx dt, some fx. So, think of it in one dimension. What you would do is t plus dt would be equal to xt plus f of x of t dt plus higher order terms, of course. I should not write dt but delta t, okay. This is an infinitesimal, I not miss. I have done the same thing, it's just the generalization. So this tells you that I should be able to tell you where the representative point is going to get to, starting from an initial point after an arbitrary time. Okay? So this is what is known in the literature as the local solvability, that in principle, if you remember, one of the objectives, or probably the main objective of dynamical system theory, is to tell you, given an initial condition, where the system is going to get to at some arbitrary time. So it's called solvability because by this procedure all dynamical systems are solvable, and it's local because what you are doing is that you are like evolving locally. You start from a point, you ask what is going to be the fate at a small time delta t, and then you start from the next point and so on. Okay? So this is in principle always possible. We will see that this is not going to happen at specific points at which f x0 itself vanishes. We will come to that, those are known as fixed points, but barring that possibility, this principle is a way of getting the phase space point at an arbitrary time is always going to work, under the assumption that the f is a smooth function and so on. So that we have already assumed that it's a well defined function, it does not have singularities and so on. But there is something else that we are after, I mean something more than that. What we want is, we want this function, if you remember, we want this function g that would tell me once and for all where the system is going to get to. Like it will be some formula where you tell me your x of 0, you tell me your t, and then I type in those numbers and I insert those numbers into this formula and I tell you at once x of t. While the problem with this method is that suppose I want to know where the system is going to get to after 2 hours, well, I have to let the computer do this computation, run this loop for maybe not for 2 hours, it depends on the computational power of the computer, but then so there is no way in which I can write down a formula for x of t. I will know where the system is going to get to after 2 hours somewhere, after 4 hours somewhere, but it will not give me this function per se. If I happen to find that function per se, this g of t, like if I happen to get that, so then I would say that the system is integrable. I will come to more precise definition of integrability when we discuss conservative systems, more precisely Hamiltonian systems, but for the time being we say that if this is possible, if g, this function is known, if g is known, then we say that the system is integrable. That then my job is done, then I have a formula, I just put in the numbers that I have. And of course integrability implies solvability, because if you know, if you have a formula that tells you where the system is going to get to after after time t, so I can put t equal to delta t, okay, in this formula, and then I can retrieve like everything that I got from this local approximation. So integrability implies solvability, but so this way it doesn't work. Like obviously solvability doesn't imply integrability. If I am able to tell you where the system is going to after 2 minutes, it will not tell me, it will not give me a general expression for I will come to more precise definitions, as I said, of integrability in later part of the course. Okay, so now you see why it is so difficult to get this function. It is precisely because these functions, this f of x, these are generally non-linear functions. Okay, maybe in some special cases, for example, for the case of a simple pendulum, which is x double dot equal to minus g by L sin theta, that becomes a two-dimensional dynamical system. I showed you the procedure. You can integrate those equations, and then you can write down one closed form expression for theta as a function of t. I plug in the value and I get for, but in general it is not possible, and especially so because these are non-linear functions. I may not be able to do it, and so I am stuck. So I have to find out what to do next. If I look at this formula, typically in dynamical system theory, you are not just interested in finding out the fate of the representative point at any arbitrary time t, but mostly you are interested in the long time limit, where the system is going to get to after a sufficient amount of time has elapsed. Not like where the system is going to get to, I started where the system is going to get to in after 5 minutes. No, I let the system, roughly speaking, what it means is that the system has some freedom. Okay, so this x can have many different values. So I let the system scan the space, scan the possibilities. Okay, so one way to see is that this is something that I was thinking, that suppose you have a potential like this. I mean, don't think of it as a dynamical system, I am just giving you one example. And suppose your particle is somewhere here. Typically you would like to know, it's not that I start off with this point, I want to know where the system is going to get to at the very next instant. So maybe I should make it flat a bit, because probably here it is going to fall off. So something like this, and somewhere here it's very flat. Let's say the second derivative is also 0. So what you would typically like to know is that in such a situation, if I allow sufficient time to pass by, does this particle fall off to this one or that one? Okay, you may ask this one. And if you ask after 1 second where the particle is going to get to, maybe it goes somewhere here. Not much. So what I do is that I let the system, scan the phase space, explore all possibilities. And so that's to say that I would be typically interested in finding out the long time limit of the solution. By long time limit, I don't mean t going to infinity. It's it's longer than the longest time scale in the system. Okay, so the relaxation time scale in the system. So let's come back to, we saw that this integrability is in general not possible for general f of x. Now let's come to this point of solvability. So I said that given a point x of 0, I can find out where the system is going to at after a small time delta t by doing this Taylor expansion, and I should be able to do it provided I find delta t small enough, sufficiently small that I can neglect higher order terms. But there is a caveat in that, in the following sense, that this is not going to work at those specific points for which f of x itself is 0. Suppose you start with a point where the local velocity itself is 0, then obviously you are not going to evolve in time. Okay? So at the next time you are going to remain there, and so on. As time goes by, you will stay put. You don't have a way to go out because the local velocity is just 0. Okay? So such points, and typically under our assumption of f of x being a smooth function and with well defined no overhangs and so on, you can say that such an equation will have only a set of isolated zeros. Okay? So the solution of this equation are what are known as the roots of this equation, right? I mean, these are, so if you solve this equation, you will find values of x at which f of x is equal to 0, and they are going to be isolated typically. It's not that so one possibility is that the function is 0 everywhere. Whatever be the value of x, f of x is 0. That's a trivial thing. Then you have we will see it arises in two-dimensional systems under specific conditions, but the local velocity is everywhere 0. But that's a trivial situation. Then you have a plane of fixed points. Okay, but in general, what happens is that you have some isolated points. Think of it in one dimension. And in fact, I will so today spend most of the time on one-dimensional systems. So you can just think of some function here and there. So these are the points at which f of x is going to be 0, right? And these are isolated. Okay. So these points, so the solution of this equation, let me denote them by x star, and these are known as fixed points. Okay, these are the fixed points of the dynamics, because if you start from there, you remain there forever. Okay, and you immediately see, if you use this equation, that if you start from a fixed point, you remain there, because this term is 0. But what about the next term? Is it still 0? Sorry? No, it will still be 0. What will be the next term? So, delta t square by 2, what will be the next term? F prime, but prime derivative with respect to what? No, so it will be f prime x of 0 times x dot. No, you have to take x dot, because you are Taylor expanding in time, right? F prime x of 0 times x dot at x of 0, and so on. And this term will of course give you the same solution, because if x dot is 0, x double dot is 0, x triple dot is 0, all derivatives are 0. If you do the Taylor expansion, you will find that each and every term in that Taylor expansion, excepting for the first term, will give you 0, and therefore x of delta t is equal to x of 0. You do not evolve. Okay? Like everything is so consistent. So today I will specialize to one-dimensional systems and look at some properties of fixed points. It would turn out that one-dimensional systems are a bit boring, but it gives you some idea of how to study dynamics around a fixed point by a method which is known as linearization around a fixed point. And I will also use these one-dimensional systems to demonstrate, or at least to show some illustrative examples of what is known as a bifurcation theory. It is a very important part of dynamical system theory. Unfortunately, due to since I plan to cover conservative systems in much more detail, I will not have time to go to higher dimensional systems. But the book by Strogatz is an excellent place to read about. I will give references towards the end. So let us specialize to one-dimensional systems. The good thing about one dimension is that it's the plots, etc., the graphs, they are like easy to plot and so on. So one can get a lot of intuition and so on. Okay, so now my equation is very simple. It's just x dot is equal to f of x, where x is just a real number. So let's look at this thing. Our general attitude will be the following: since we know that in most cases we will not be able to solve that equation for a general nonlinear f of x, our attitude will be to try to extract as much information as we can by plotting the function and doing simple things like Taylor expansion and so on, because we know that we are stuck, we cannot solve that equation in general. Okay? So one thing is, if you are given a function f of x and x, you just plot it. Okay? You plot it by hand, as Mustansir was saying. It's important that, and I'll show you some simple tricks to plot functions by hand. I mean, you don't have to necessarily do GNU plot and so on. So let's say you have a function like this, something. I just drew a random. So you see that these are your fixed points, because these are points, fixed points by definition. So I'll use the abbreviation FP for fixed points. So fixed points satisfy if fixed points x star, they satisfy f of x star is equal to 0. So you see that you have a fixed point here. Okay, so let's you have a fixed point here and you have a fixed point there. Okay, but this plot is telling you something like more than that. Of course, it helps you to locate the fixed points, and this is in fact one of the simplest way to locate the fixed points, to just plot the function and see where it intersects the x axis. But this is telling you something more than that, that the following thing should be evident, that suppose I am at a value of x which is slightly to the right of this x star. So I have drawn this point too big, maybe me draw it slightly small. Suppose I am at a point at an x slightly to the right of x star. So this is my x star. Then I see that f of x is negative. So this means that the velocity is negative. Okay? Velocity is negative means if I start with a point slightly to the right, I will be brought back to x star because the velocity is not in the positive direction, it's in the negative direction. Okay? So what I will do is that I will just put an arrow here to indicate such a fact that the while on this side what I see is that the velocity is positive. That is, if I start with a point somewhere here, I will be pushed towards x star, right, because the velocity is positive. So, in one dimension, the axis itself is giving you some kind of an arrow direction where the velocity is going to point to. And if the velocity is this way, then x is going to increase. If the velocity is this way, the x is going to decrease. So, I will put an arrow on this direction. So, this tells you, this should tell you something, namely that definitely this point is a stable fixed point. Think of the analogy that we must have learnt in school days, the definition of a stable fixed point and an unstable fixed point and a neutral fixed point. A stable fixed point is one in which if you make a small perturbation like away from it, you will be brought back to that point. While an unstable is one in which about which if you make a small perturbation, you are going to fall off. And a neutral is one where nothing happens, it just rolls on. So this is definitely a stable fixed point, and it is going to also tell you that whatever be the value of x that you start out from, so long as it is to the right of x star, as time passes by in the long time limit, you will be approaching x star in the long time limit. That is going to be the long time fate of the representative point. So since it's a stable fixed point, the convention is to denote it by a filled circle. Let's look at this point now. Here you see the velocity, if I am to the right of this x star, so this is also an x star. If I start off to the right of x star, then the velocity is, it's positive, right? So x is going to increase in time. Okay, so if I start from somewhere here, then at the next instant I will be thrown towards the right because x is going to increase. So I put an arrow this way, and the opposite is going to happen here, that if I start from an x which is to the left of x star, the velocity is negative, so x is going to decrease. So I will put an arrow here, and this shows that this point is unstable. It is unstable in the same sense as this one. If you make a small perturbation, you are going to go this way. If you make a small perturbation to the right, you are going to go that way. And the convention is to denote a unstable fixed point by an unfilled circle, like an open circle, as I have seen. So you see that just by drawing the function, you can get so much information about the system, and not just that, you were after, you wanted to know where the system is going to get to after a long time, and just this plot is telling you enough information. Okay? So now we will see how to develop a mathematical theory. It should be like obvious that if I start from a point very close by, then I can do a Taylor expansion about the fixed point. So this brings me to the theory of this linearization about. So this picture is clear, right? That why x star is, x star is, it can be either stable or unstable. We will see that in one dimension these are the only possibilities. Okay, there is a possibility where a point can be half stable, but I'll come to that also. This one. You see, what is this graph fx? But f of x is nothing but x dot, right? F of x is by definition x dot. So if f of x is positive, that means x dot is positive. If x dot is positive, that means the velocity is positive. It's a one-dimensional line. So positive means you are going, x is increasing in time, and negative velocity means x is decreasing in time. That's it. You have to always remember that f of x is a very special thing. It's the local velocity. Huh?
I forgot x.
Okay, x dot.
X versus t graph would give you the velocity change.
No. Okay, okay, so this is the method of linearization. So in one dimension it's very simple. So remember how I argued, I said I take a point which is slightly to the right of x star or slightly to the left of x star, and I ask where the point is going to get to as time goes by. Okay. So I have this equation x dot is equal to f of x, and now I know that there is a fixed point at x star. So what I do is that I add a small perturbation, like small fluctuation. I start from a point slightly like away from x star. Okay, in my notation it's delta x of t. So this is my x of t, and I want to know how does this x of t behave as a function of time. Okay, so this is simple. So I just use these equations. So what I get is x dot of t, that will be x star dot. Okay, so let's say I plug this whole thing on the left hand side. So I get x star dot, but x star dot is 0 by definition. Okay, so I get 0 and I get a dot here, so which is giving you delta x, how do I write, dot, right? But then this should be also equal to f of what is x? X is x star plus delta x of t. And since delta x is small, so I am looking at the behavior of small fluctuation. Delta x of t in magnitude is much smaller than 1. I can do a Taylor expansion, and if I do a Taylor expansion, the first term that I get is f of x of star, but that is 0 by definition, because x star is a solution of f x equal to 0. And the second term will be f prime of x star delta x plus higher order terms. Don't have to write it, but let me write it at least once, and so on. So remember, see this one, this is just a number, this is not a function. You take the derivative of f of x and evaluate it at x star. So this is just a number, this is not a variable, and so is this one, and all the other so Taylor coefficients. So long as f prime of x star is not equal to 0, so long as this term is not equal to 0, I can always choose a delta x small enough such that I can neglect higher order terms. If f prime x star is itself 0, then we will end up with what is known as a hybrid or higher order fixed points, that I will come to later. But the typical situation is that f x star is 0, but the derivative is not 0 there. Okay, so then I can, so long as this is not equal to 0, then what I can do is that I can neglect, I am not writing these things, this takes time. So then I can neglect higher order terms, and I will end up with this equation delta x of t. So dot means just d dt of that is equal to some number. This is just a number, it could be positive or negative, okay, some number. So let me call it lambda, and delta x of t, neglecting higher order terms. So it is approximately equal. Or to put it differently, I can always find the delta x small enough that such an expansion is valid. This equation is valid. Now this is a very simple linear equation. There is no non-linearity here, and I can at once solve this equation. So can somebody tell me what is the solution of this equation? Sorry, can you speak up, because it's no, delta x of t is equal to e to the power lambda t time, remember lambda is a number, it is constant, times delta x of 0, right. So, this tells me that if lambda happens to be positive, then this fluctuation is going to grow in time, and therefore, the point that I start out with, the x star, the fixed point that I start out with is an unstable fixed point in the same sense as it is here, that if I start from somewhere here, delta x is 1 millimeter initially, but as time goes by it becomes 1 centimeter, 1 kilometer maybe. Okay. So, if lambda is positive, write it this way, then I would say that the fixed point that I started out with is an unstable fixed point. And if lambda is negative, then I would say it is a stable fixed point. And obviously, if lambda is 0, by my according to my way of doing things, I said that lambda cannot be 0, because if lambda is 0, you have to take higher order terms. It no longer remains a linear system. So, let us for the moment forget about this particular situation. So, if lambda is positive, it is an unstable fixed point. If lambda is negative, it is an stable fixed point. And remember what lambda is. Lambda was what? Lambda was f prime x star. So, it just tells me that if the local velocity is positive, I have an unstable fixed point. If the local velocity is negative, I have a stable fixed point, and that is very much consistent with what I have drawn here. So, for example, at this point the local velocity is, it is the tangent to this curve, it is like this way, and here the tangent is like this way. So, you can check that it works out that in one case here the velocity is indeed negative, and therefore, you are pushed to that point, while in the other case it is the other way around, and therefore, you have an unstable fixed point. This tells me what is going, this theory tells me what is going to happen in a small neighborhood around x star, that you are going to either grow exponentially in time or decay exponentially in time. It does not tell me what is going to happen far away from these points, but from continuity I can say that look, here is a fixed point and here is a fixed point. So, let me just blow up this section here. So, this is just a blow up of, so here is my stable fixed point, here is my unstable fixed point, and I know what is going to happen here in a small neighborhood. It is an unstable fixed point. So, the arrow directions are like this, fluctuations or perturbations are going to grow exponentially in time according to this theory, and I know in a small neighborhood here what is going to happen, that perturbations are going to decay in time. It does not tell me what is going to happen here, but you see I do not have much freedom, because if I the flow has to be there has to be continuity, there is no fixed point in between. So, I can safely say that in between also the flow direction will be that way. It is just that if I start somewhere here, I will not be able to say that the decay will be exponential. It will be exponential only if I start in a sufficiently small neighborhood, but I can definitely say where the system is going to get to after an infinite time. Namely, if I start somewhere here, after it will approach this point. Okay, so this is something that I will keep. It's a limiting process. It doesn't. Infinity is something that you can define. That okay, at 10 o'clock it will get there. Not like that. It will approach the difference between your actual phase space point and this point will keep on decreasing as time goes by. It will think about linearization, which. Let me just illustrate it with some simple examples, and also we will have an idea of, I think this many students find it difficult to draw plots, to draw figures and simple functions, plot simple functions. So, we will see how this works. And by the way, according to this procedure, if f prime x star is equal to 0, then linearization doesn't give me any information. I have to go beyond linear terms. I have to keep higher order terms, because the second order term is indeed the first non-zero term in the Taylor expansion, and I better keep it because the previous terms are 0. When the previous terms were not 0, I could. So let's do some examples. So example, let's say this one, x dot is equal to, let's say, x square. I'll show this case of, no, let me do this one first. X dot is equal to x cube, x dot is equal to minus x cube. Okay. So remember what I have to plot according to that theory. I have to plot f of x, which is x dot, and here f of x is x cube. Okay. So I plot f of x, which is nothing but x dot, as a function of x, and this function like obviously goes through 0. Okay. So if I put 0 here, I get x dot equal to 0. That means 0 is a fixed point. Okay. So 0 is a fixed point. So here I have a fixed point. I don't yet know whether it's a stable fixed point or an unstable fixed point. Now what I do is that x cube, so what is going to happen, it's going to be very flat here, but then like eventually it will diverge, because as x goes to infinity, this will go, and this is an odd function, so it will do something like this. If I just follow that procedure, then can somebody tell me what kind of fixed point is this one? I just look at if x dot is positive or negative and so on. Sorry? Unstable. Right? This is an unstable, because here this velocity is positive. You'll be, and suppose x dot were negative, so which is here, then the function is just a reverse. Can somebody tell me? Can one of the students tell me why the function is so flat here at x equal to 0? I have drawn it to be quite flat here. The first derivative is 0, also the second derivative is 0. So the curvature is not there. Okay, and here this will be just the opposite. So again x dot as a function of x. So here is a fixed point, because if x is equal to 0. Can somebody tell me what kind of fixed point is this one? This is a stable fixed point, right? Because here the velocity is negative. So if I start from somewhere here, I will be pushed towards that point, right? So here is this, and according to my notation, it's. But here are two examples where linearization is not going to work. Why? Because f of x star, f prime of x star is equal to 0. Because so what is f prime of x? F prime of x is, let's say in the first example, it's 3x square. So f prime of x star is equal to 0, and not just that, f double prime of x star, that also is equal to 0. So linearization doesn't work. Yet I can gather some information about where the system is going to get to by drawing this simple curves. Okay. Linearization would have worked if this were a function for which f prime of x is not equal to 0. Let me show two other examples where what you get is a half stable fixed point, and we will show how those half stable fixed points arise from dynamics, from what kind of dynamics we give rise to. So one example is x dot is equal to x square. Here also linearization is not going to work, because if you do Taylor expansion, there is no linear term, right? This is already quadratic. Okay, so there is no linear term to, like again x equal to 0 is a fixed point. So let me then again draw this x dot as a function of x. So this is going to be what? This is just a parabola, but you have to be careful not to make it flat at x equal to 0, because the second derivative is not 0. So twice x, second derivative is 2, it's not 0. can, so I have a fixed point here according to my rule, but what kind of fixed point is this? Like, is it? So tell me, on this side it's positive, so it's going to be thrown away. On this side? Huh? So on this side it is what? The velocity is positive. So x is going to be less negative. If I start from a point here, I have to add dx dt, right? So x is going to be less negative. So the flow is here. And this is quite unlike the cases that we had discussed, or this is neither stable nor unstable. It is stable so long as I start from, it is unstable so long as I start from an x which is to the right of x star. So I better fill that part with, what was my notation? No, I should keep that part blank. I fill this part, so this is what is known as a half stable fixed point. It's neither stable nor unstable. It's stability depends on which direction you are approaching. Half stable fixed point. Similarly, if you draw x dot is equal to minus x square, you will also see that you will get a half stable fixed point, which is just the other way around. So I use these examples to show that linearization is not always going to work. If you don't have a linear term, if you do an expansion, it's not always going to work, but plotting is definitely going to work. If you just plot those functions, you know where the roots are, and you know also from these examples that if you have a stable fixed point must have just following it an unstable fixed point. So stable and unstable fixed point must alternate each other. Because that's why it is called a stable fixed point, right? Because it's a stable, because in the neighborhood you are going to flow towards it. That means there must be an unstable fixed point somewhere, if f of x has more than one root. I will come to that if it is not so clear. But at least this part should be clear, that linearization is going to work when there are linear terms, and even if there are no linear terms, you can still draw the function and find out where it is going to get to. So now is there something else that, now I tell you something which is not possible in 1D. So in 1D we saw that at least in the neighborhood of fixed point, solutions are either going to grow exponentially in time or decay exponentially in time, and it can be shown from from theories of differential equations, that in 1D these are the only possibilities, like trajectories either grow or decay. You cannot have oscillations in 1D. So let me just explain that. So you cannot have oscillations, and I will explain what do I mean by oscillations. Oscillations in 1D, this is an important fact of life. So it says all trajectories grow or decay monotonically in time or stay fixed monotonically in time or stay fixed, or stay fixed. So I either you start from a point, and if you plot x of x as a function of t, so what it shows is that what it says is that you either grow or you decay or you remain the same. Can you tell me at which point, if I start from that point and if I plot x as a function of t, which point will give me such a figure? X of t, what sort of point do I have to start out from, so that if I plot x as a function of t, I am going to get a line like this, stable fixed point, right? So if you start from a stable fixed point, you don't grow or decay, you just stay there. While if you, so this is a not stable fixed point. If you start from fixed point, you don't. If you start from a stable fixed point, Well, if you start exactly from the fixed point, you remain there, but like either way, you either grow or decay, but oscillations are not possible. So, let me just tell you briefly why you cannot have oscillations. So, you may have such a situation, or you may have a situation where x as a function of t is you start from some initial value, it grows, or you start from some initial value and it decays. These are possible. These are possible solutions, but what do I mean by oscillations in 1D? What I mean is the following: you cannot have a situation like this, not even damped oscillations. This is also not possible. Neither this nor that. You have either a growing solution, need not be exponential, it will be exponential only very close to the fixed point, or you stay put, but not like that. So, let me just say why it is so. So, can you turn on the AC? Maybe I should. It's very hot out here. So, the point is the following. So, let us again go back to our. You saw that this linearization procedure has. Yeah, thanks. Yeah, at the moment there is no sound or anything. I think it had to do with the battery. Probably this is. Yeah, make it like. No, not 26, make it to 20 or something. Okay, so you saw that this procedure of linearization has limitation. If the function, if you have a, if you don't have linear terms, then you cannot rely on linearization. It's not going to. But this plotting is definitely going to work. So let me just plot f of x against x and show you, at least topologically, or not topologically, I mean just by some simple argument. So you have these fixed points. These are your fixed points, and some of them will be stable and some of them will be unstable, and you may check quite easily that a stable fixed point is followed by an unstable fixed point, followed by a stable, unstable, and so on. So what it means to have oscillations? It means that, let's say, so I need an unstable fixed point. Which one is unstable? I guess this one is unstable, right? And this one is therefore stable. Right? This is unstable because if I start from somewhere here, I will be thrown to the right. So this is unstable, so this is stable. What it means to have oscillations? It means if I start from somewhere here, so once I go that way and then come back, and then that way and then come back. That's what it means, that x is going to increase and decrease, increase and decrease, increase and decrease. Why that is not allowed? Because I have assumed this f of x to be a single valued function. At every point, f of x is going to have just one value which is independent of time. Had this been a non-autonomous system where f of x is a function that has explicit time dependence, once it is telling me that the local velocity is that way, so I flow that way, but then at the next moment the functional form changes and it is going to push me this way, then I would have had such a situation. But here it is simply not possible because the function once given to me, it is set. I mean I cannot do anything. So if I happen to flow in one direction, it cannot happen that at a later time I start moving in the other direction. Not even damped oscillation, no oscillation is possible. So there is this thing that we have all heard that simple harmonic motion exhibits oscillation, we say. What is, but like isn't simple harmonic motion also a one dimensional motion? What's going on? Just now I said that you cannot have oscillations in 1D. What is the problem? It's two dimensional, right? Because you have to give the velocity and the position. It's not one equation, right? mx double dot equal to minus kx. That's not my definition of a dynamical system. You have to break it into two first order differential equations, x dot and p. Okay, x dot is equal to you know how to do. So that's everything is fine. So you cannot have oscillations in 1D, and you may have only trajectories in 1D. So 1D is kind of very boring. You have either stable fixed point or unstable fixed point from linearization, or if not stable or unstable, you may have a hybrid situation, this half stable fixed point. But that is it. And it's precisely because you are moving in one dimension. You don't have much freedom. You either keep walking to the left or keep walking to the right. You don't have possibility of going back and forth, as I showed. There is no second dimension in which I can make a detour and then come back. It's not possible. It's just 1D. We will see that in 2D things become much more interesting, and that's something I'll come to towards the end. But there is one particular feature of 1D systems, or there is one particular thing that can be illustrated with 1D systems simply. That's what I'm going to do in the next, and that's this thing of, by the way, so there is this example that I found on the net. Can somebody tell me, it's just a simple thing, I mean, just for fun. Can somebody tell me what are the fixed points of that equation? 0 and pi, that's it? N pi, right? So x star is equal to n pi, where n can be 0, plus minus 1, and dot dot dot. And we know, hopefully we know how to plot this function. It's this way, and it's that, right? Okay. What sort of fixed point is this one at x equal to 0? So here the velocity is positive, we are going to this way. Here negative, x will become more negative. So this is an unstable fixed point, and as soon as you have drawn this one, you know what are the other fixed points going to be. This is going to be a stable fixed point, this is going to be an unstable, and this is going to be a stable fixed point, and so on. This will be unstable, and therefore this will be stable, and therefore this will be unstable. So you see very simple arguments like that of continuity and plotting the function. It tells you a lot about such systems in 1D. You don't have to do much. You have to just plot and just find out where the local velocity direction is. Okay, this is just a small point. Okay, so now I come to what is known as bifurcation theory. So the bifurcation theory is the following. Let me illustrate it with 1D systems. I probably will not have time to go to, well, I'll show something. No, not in 2D, I will probably not. So this is my 1D system, f of x dot is equal to f of x. Okay, now this function, it's a function of these dynamical variables, but it may depend on certain parameters. Okay, let's call that R. For example, we know that let's say for the simple harmonic oscillator, there are parameters like G and L and so on. They are not dynamical variables. Why they are not dynamical variables? Because the length is given to you. It's not that you are allowed to, the length is not changing as a function of time, because you have not been supplied with an equation of motion for the length. Okay, so it's not a dynamical variable, so to say. Similarly, G, the acceleration due to gravity is given to you. It's 10 meter per second square. It's not changing as a function of time. So these are not dynamical variables. These are parameters, and these are dynamical parameters. Why dynamical parameters? Because they determine your dynamics. I mean, they are parameters in the equations of motion, not just some arbitrary parameters. These are parameters that tell you what the dynamics is going to be in time. Okay? So I have denoted such a dynamical parameter by R. It may happen that there are more than one parameter. I have just taken the simplest situation where there is just one dynamical parameter, and in fact, for bookkeeping, I mean, like if I were careful, I should have kept on all those equations that I had written down until now. I had kept those parameters. I should have kept those parameters, but they are there. They are for the simple harmonic oscillator. One dynamical parameter is the spring constant and the mass and so on. Now it may so happen that I have a way to tune this parameter by hand. So somehow I have been given a knob that allows me to tune that parameter. So, it is an experimental thing, and it may so happen that by tuning that parameter, what I do is that, or not I do, the system decides to do, is that there were no fixed point and suddenly a fixed point springs up from nowhere. It gets created out of the blue. Or it may so happen that a fixed point which was stable for some values of r, as I jack up the value of r, that stable fixed point became unstable, or an unstable fixed point became stable, or a half stable fixed point became fully stable fixed point, and so on. Okay? So, there are these different situations that may happen as I tune this dynamical parameter. So, this is a parameter that I have in my hand. This is a knob, experimentalist knob, and as we will see in the equilibrium statement also, it is a very very handy thing. It lets you allow the possibilities which are offered by this particular dynamical setting, that okay, it is stable so long as r is positive. If r becomes negative, it becomes unstable, and so on. So, this phenomenon is known as bifurcation. So, we will see why it is called. So, bifurcation, very simply put, it is just a qualitative, it is a qualitative change, it is not a quantitative change. I would not say that the function was, the point was stable, but the exponential growth was like e to the power lambda t, and now when r became slightly larger, now it is like e to the power 2 lambda t. I would not call it a qualitative change, it is a quantitative change. The approach to the fixed point became doubly fast. I would not call it a qualitative change, it is a quantitative change. A qualitative change is one in which the nature, the behavior of the flow changes drastically. Okay? So, I would say a bifurcation is qualitative change in the dynamical behavior of the system. Let me put it this way. See, when I write these definitions, I mean, don't take them to be pristine and sacred or something. It's just, maybe there are more mathematically rigorous definitions. I mean, this is just to fix our ideas. So, qualitative is the key word, qualitative change in the dynamical behavior of the system as some dynamical parameters are tuned. On tuning some dynamical parameters, I am not writing like as you tune some dynamical parameters, this is the experimentalist now, and the point at which, or the value of r at which you see this changeover, r, there is a critical value, I would use this word, there is a critical value below which you have some behavior, above which you have some other behavior. So, that particular value of r is very special. So, we would call it a bifurcation value or a bifurcation point. So, let us see some examples. The best way to appreciate this is to see some simple examples. So, it turns out that in 1D you may have only 3 basic types of bifurcation, and I will show you why you have just 3. Well, that I may not be able to show, but I will show you what are these 3 types. And so, the first one is what is known as saddle node bifurcation. I will tell you why it is called saddle node. First, let us understand what this bifurcation is all about. Okay. So, the simplest example is x dot is equal to r minus x square. This is a non-linear function, r minus x square x dot, and r is the dynamical parameter. Okay. So, what are the fixed points of this dynamics? Is x equal to 0 a fixed point? Yeah, x equal to 0 is not a fixed point, because if I put x equal to 0 here, I do not get x dot equal to 0, right. By the way, so this is my f of x of r by definition. So, my x star is going to be what? X star will be plus or minus square root of r. Just at this level, you at once see that if r is negative, you are not going to have a fixed point, because square root of a negative number is imaginary. and x is a real number by definition because it's some dynamical real physical variable. So this tells you that it should be that the fixed points exist only for positive r and none for negative r, and there is a fixed point at 0 for r equal to 0. So let me just take again, I should draw the plots, and that's the best way to x dot equal to r minus x square. So let me plot it for r equal to 0. So the way to plot it, it's very simple. So if r is equal to 0, very close to x equal to 0, you can forget about x square. So very close to 0, x dot is just r, which is a positive number. So somewhere here you get, this is r, this distance is r, and then as x increases, you have a parabola. So okay, this should be symmetric about x equal to 0. Okay. Now you see that you have two fixed points, one here and one there. Can one tell me what kind of fixed point is this? And on this side the velocity is negative, it is going to push you this way, so that way. Here it is positive, it is going to pull me towards the fixed point. So my definition is, according to my convention, this is a stable fixed point. Let me get rid of this 0, let me write it short. And what about this one? See here x is positive, so it is going to make it less negative. If I start from an x here, dx dt is positive, I am repeating these things because these are simple things, but you know it helps to say this in words. I mean, sometimes instead of writing formulae and so on, so it's going to give me this way, and here it is negative, so it is going to make x more negative, so it is going to push it away. So this. Okay. So there is a stable fixed point and there is an unstable fixed point. Let's see what happens when r is less than 0. And by the way, this matches with this one, that if r is positive, I ought to have two fixed points plus minus square root of r, and these are the two fixed points. Now what happens when r is negative? When r is negative, close to x equal to 0, I have a negative intercept. This is minus r, and then I have an inverted parabola. Okay, so this is x dot. You can call it fx also as a function of x. Now can you tell me what are the fixed points? Is there a fixed point at all? There is none, because this function doesn't ever cut this x axis. There is no fixed point. What's the flow going to be like? The flow is going to be like, so it is this way, so it has to be this way. There is no fixed point, right? If I start from somewhere here, so dx dt is negative, so x is going to decrease in time, but that's it. There is no fixed point at all. So you see, I started off with two fixed points, one of them was stable and one was unstable. I ended up with a situation where there is no fixed point when r is negative. And what happens when r is precisely equal to 0? When r is precisely equal to 0, then what I have is, I have x dot equal to minus x square, which is just an inverted parabola passing through the origin, and I have a fixed point here, and now here it is going this way and there it is going that way. So now what I have is, I have a half stable fixed point. Okay. So such a bifurcation, so first of all you understand that why there is a qualitative change, because r is the parameter that I am tuning. So long as r is greater than 0, I had two fixed points, and as I start decreasing r, what is going to happen is that you see that these two fixed points start approaching one another. Why do they start approaching one another? Because this is square root of r. So as I decrease r, the two fixed points start approaching each other, and then they coalesce, they give rise to a half stable fixed point, and then that's it, they annihilate each other. Okay, nasty guys, right? I mean, they come and they hit each other and that's it. Okay, so such a bifurcation, it would not be clear why it is called a saddle. I mean, in 1D It's difficult. There is no saddle. We say, so saddle means there is one direction in which you flow towards and there is another direction in which you flow away. It's just a one dimensional system, so there is no second direction, but it's called a saddle node bifurcation, and there is a standard way to denote it. So the standard way to denote it is by what is known as a bifurcation diagram. So here what you do is that you plot your fixed points as a function of r. Some of them will be stable, some of them will be unstable. You plot everything that you have. So you see that so long as r is greater than 0, you had two fixed points, namely x star equal to plus minus square root of r, which means x star square is equal to r. So that's the equation of a parabola. Okay, so there is one parabola branch here and one parabola branch here. This is x star equal to plus square root of r. This is x star equal to minus square root of r. Okay, so this is r equal to 0, and there is no fixed point on this side. Okay. Now one of them is going to be stable and one of them is going to be unstable. You know which one is stable. The one which is x star equal to plus square root of r is stable. So the way to denote it is this way, that you draw a kind of a so solid line for the stable branch and a broken line for the other one. So you have two fixed points. They get created out of nowhere because there are no fixed points for r less than 0. There is a fixed point which is half stable at r equal to 0, and they kind of split apart, and then there is one stable branch and one unstable branch. And in some books, somewhat confusingly, they draw the flow lines here. It's a bit confusing, but let me just show you what do they mean. So they do something like this. It just shows that if you, it's kind of confusing because here you are plotting x star, but what it means is just the following, that since it's a stable fixed point, if you start from an x which is smaller than x star or larger than x star, you are going to go there, while here you will be repelled like away from this one, and on this side of course there is no fixed point, so it's just that. So it's called a bifurcation diagram. So it's called saddle node bifurcation. If you read Strogatz's book, there were two gentlemen from US. I mean, people from America. Sometimes they come up with very nice names and kind of like imaginative names. So instead of calling this a saddle node bifurcation, they call it bifurcation out of the clear blue sky. Not just out of nowhere, out of the blue. It's a clear blue sky. There was nothing here, and suddenly you got two fixed points. Okay, so now you can imagine what are the other possibilities that can happen in 1D. You had two fixed points, they came and they just do this and then like annihilate. One possibility could be that you have two fixed points and then they come and meet and they are very gentlemanly, so they exchange their attributes. A stable and an unstable came together, and then the stable one said, okay, let I be unstable and I make you stable. Okay, this is one possibility. The other possibility is they become friends. So there is a stable and an unstable, they come, so there are two stable fixed points and they come together, and you have one stable fixed point that remains. Okay. So this saddle node bifurcation is the only bifurcation where these fixed points get like annihilated. But there may be a situation where they remain for all values, it's just that two become one. Okay. So that's the next one, which is called the transcritical bifurcation. I'll be fast in these parts because you have to just draw these figures, you know how to do it. You have to just draw and find out the fixed points and the flow around that.
Technically correct if I draw a graph for both the positive and negative values of r. For positive, if r is positive, that is the real axis, x star.
Like everything is real.
But for negative value of r,
No, this is not negative value. So no. For negative value of r, x is imaginary. So there is no x star here. No, here it is not, R is not negative on this side, no? R is positive. Huh? Sorry? No, but I am plotting x star as a function of R. X star I am plotting. So x star has got two solutions, plus square root of R and minus square root of R, only for R positive. For R negative, there is nothing. I haven't drawn anything. These lines, forget about that. They make you feel so confusing. So if you forgive me, I'll remove them. They just tell you how the flows are going to be like. If it's a stable, by definition, it is going to pull everything towards it. If it's an unstable, it is going to push everything away from it. That's it. I'm plotting x star as a function of R, not x dot as a function of R. Huh? X dot as a function of R, I did not do. I plotted x dot as a function of x. I found out what are the fixed points, and now I am plotting just the fixed points as a function of R. Okay, so there is, okay, before I go to the next one, actually for the remaining two examples I will be very fast, but let me just tell you there is another way to look at this one. See, x dot is equal to R minus x square, so you can call it, so this allows you to define a potential function v of x. X dot is equal to minus dv dx, probably like Mustansir will cover, this is like this overdamped equation. Well, there is no noise, but this is the overdamped equation. You can think of the situation where there is a ball which is moving in a potential v of x, and this whole system is put in a very viscous medium, like let's say what is a very viscous? Glycerine or some good, for example, for those coming from Calcutta, this is the winter time, this gooder shondesh that you get, like khejur good and so. It's so viscous that the particle is like unable to accelerate. It just sees where the potential, it just flows downhill. If the potential like allows you to move down, allows the particle to move downhill, it just moves downhill. So you can also do it this way, and then v of x will be what? V of x will be R of x. Let me put the sign later. So what will be this? So this will be that, and this will be that. Huh? So if you plot those v of x, you will see that your fixed point is actually the minimum of that potential. Huh? I am not drawing it, so try this. It's very simple. So this procedure is okay, right? This x dot is. It will probably become clear if from Francis' lecture on Langevin equation. Let me quickly get to the second type, which is called the transcritical bifurcation. Transcritical bifurcation. So this happens, you see there I had x dot is equal to R minus x square, and there I saw that there are situations where there are no fixed point at all, but there may be dynamical systems where a fixed point always exists. You cannot annihilate, a fixed point, it exists for all values of R. It may change stability, but it may not happen that a fixed point just disappears. So the situation is, this is, suppose you take this one, x dot is equal to R x minus x square, and this is what? This is R of, this is x of R minus x. So that means you are going to get two fixed points. One is x dot equal to 0, and one is x dot x star equal to R. Right? Let me quickly draw the figures. I will not go into details because these are simple functions to plot. So when R is greater than 0, if you plot x dot as a function of x, so how to plot it? Well, very close to x is equal to 0, this is the term that is going to dominate. So it's a linear dependence, right? So it's going to give you a straight line. So R is greater than 0, so it's going to give you a straight line, and then like eventually it is going to be minus x square, and then this way. So here I have a fixed point. Let me draw, here I have another fixed point. This is a stable one, this is an unstable one, and the flow is like that. This is R greater than 0. Let me now draw it R less than 0. r less than 0, you still have a linear dependence close to x equal to 0, excepting that the slope is now negative. Okay, I had a positive slope there, I now have a negative slope here. Eventually it will be like this, and this will be like, okay. So you have one fixed point here, one fixed point there. I am plotting x dot as a function of x, and you can check that now the flow directions are this becomes stable, this becomes unstable. So this way. And what happens exactly at r equal to 0? So when r equal to 0, again I am plotting x dot as a function of x. So if r is equal to 0, I have just an inverted parabola. So now x equal to 0 is a fixed point, but it's an unstable fixed point. So typically, like whenever you see a half stable fixed point, whenever you see a half stable fixed point, and you see how this what is happening at r equal to 0, you don't have any linear term, because r equal to 0 is giving you this half stable fixed point. You don't have a linear term, you have a higher order term. Okay, so I will not have time to explain this, but in the bifurcation theory, this is what is they do what is known as an unfolding of a fixed point. If you see a fixed point, a stable or an unstable, if you see that your linearization is unable to give you a stable or a half stable fixed point, but it is emerging out of some non-linear process. So what you do is that you say that this x square, this term, this minus x square, it's not, if Rx is equal to 0 and you have x dot is equal to minus x square. So what you say is that on the right hand side, if I had written down a general polynomial, this is not the first term that I would have had. First term would have been a constant that could be gotten rid of, and this would have been the leading term, and this would be the second term. So what you then do is that you take this to be a small parameter, and you show that a half stable fixed point emerges out of coalescence of two stable and unstable fixed points. If this is not clear, then forget it, but at least this should be clear that here the situation is very different from what we had in the case of saddle node bifurcation, that a fixed point exists for all values of r. You had two fixed points, they became one, but then see, so suppose you are tuning your r from r greater than 0 to r less than 0, then what is going to happen is that they merge, they become a half stable fixed point, but then they exchange their stability. The stable one became an unstable fixed point, and the unstable one became a stable fixed point. So this is what is known as a transcritical or an exchange of stability bifurcation. So this is transcritical. And now if I draw the same figure that I had drawn previously, namely x star as a function of r, the bifurcation diagram. What will be the bifurcation diagram for a transcritical bifurcation? So what I have to do is I have to plot x star as a function of r. I know that there are two kinds of fixed points, x star equal to r and x star equal to 0, right? So x star equal to r is this line, x star equal to 0 is this line, and x star equal to r is that line. Now I have to denote which one is fixed, which one is stable and which one is unstable. So I have it here. Let me just draw it. So when r is negative, the 0, 1 is stable, this one is unstable. So the 0, 1 is stable, and this I should draw by broken lines. This is unstable. And they just exchange stability. So when r becomes larger than 0, the fixed point at x star equal to 0, that became unstable, and this one became stable. So it's an exchange of stability bifurcation or a transcritical bifurcation for obvious reason. The last one is a pitchfork bifurcation. So just to tell you once more, in the in the saddle node bifurcation, there were two fixed points, they collided against one another, they annihilated one another. Here they don't annihilate, they just exchange their roles. And the third one is that they come together, they become friends. Two stable fixed points come together, become friends, become one. Okay, that's the last one. And then we are done. So this is the pitchfork bifurcation. Let me do this one. So pitchfork. I'll tell you towards the end what's the importance of these bifurcations. So now you have x dot is equal to Rx minus x cube, okay, instead of x square. So you can convince yourself that the fixed points are x star equal to 0 and plus minus square root of r. And again, this fixed point is not going to exist if r is negative, while this one is always going to be there for all values of r. So if I just plot these three, so x dot as a function of r, x dot is a function of r, is a function of r. When r is, let's say, negative, when r is negative, then very close to x equal to 0, it's linear with a negative slope. So that is this one. So it's a negative slope, and then it becomes that, because x cube will dominate for large x, so that is going to happen here. Here what is going to happen is r is equal to 0, so it's just the function x cube, which is, and very flat here, and then this. This is for r equal to 0, and what happens for r greater than 0? When r is greater than 0, then you have close to x a line with a positive slope. So here I have a line with a positive slope, and then for large x it has to go like minus x cube, and then for large negative x it goes to infinity like this. So you have one fixed point here, one there, one here, one here. You can like easily check that this is a stable fixed point. R x dot as a function of sorry. Okay. So this is a stable fixed point. So is this one, and so are these two. This is stable. This is stable, so, and this is unstable. So you see what is happening now, that you had two stable fixed points, they came together, became friends, and became one stable. They did not annihilate or exchange their roles. And here I should draw the bifurcation diagram. So I plot x star as a function of r. So when r is negative, there is one fixed point, stable fixed point at x equal to 0. So I have this line. When r is positive, so this is r greater than 0. There are two fixed points symmetrically placed like about x equal to 0, and those fixed points are given by x star equal to plus minus square root of r. So that's the equation of a parabola. So let me just draw this parabola, and one of them is going to be stable and one of them is unstable. Actually both are stable, and the fixed point at x equal to 0 is unstable. So this I draw with broken lines. Now you see why it is called a pitchfork bifurcation, because it has the shape of a pitchfork. Okay? So you have one stable branch splitting up, bifurcating into two branches, both are stable. Okay? So pitchfork bifurcation, transcritical, and saddle node bifurcation. It turns out that in 1D these are the only basic or like elementary bifurcations that can happen in 1D. in 1D flows of this sort. What do I mean by the fact that they are basic, or they are the like elementary bifurcation? There is a name for it. They say these are the normal forms of bifurcation that are going to take place or going to be exhibited by 1D system. What do I mean by that? I will probably have one example in the tutorial to like illustrate this. What I mean by that is very simple. It just means that in 1D system, whatever be the dynamical form, whatever be the dynamical set of equations, if f of x, whatever form it takes up, if I go very close to a fixed point, and if I try to draw the bifurcation diagram, or put it differently, if I go very close to a fixed point, and in a small neighborhood around the fixed point, if I do a Taylor expansion around the fixed point, the flow is going to look like either a pitchfork bifurcation, or a transcritical bifurcation, or a saddle knot bifurcation. Okay, not very far from, not 1 kilometer from the fixed point, but if I go very close, I will show this in the tutorial with an example, that it's guaranteed, and there are theorems that I will not prove, can be shown that these are the only 3 basic forms of bifurcation, normal forms of bifurcation that can happen in 1D. So let me then. Yeah, so if it is an fx, so what you do is that typically what you would have is, you would have x dot is equal to fx. So what you do is that you locate the fixed points and do an expansion around that fixed point, and it is going to be look like either this or that or that. Huh. Huh. Yes, exactly. Yes, exactly. Yes, exactly. Yeah, I'll show this with an example that you go, and these are the leading forms. That's what I meant, that if you go very close, the leading form will be like this. Okay, so let me then stop at that. Thank you. So I think in earlier this bifurcation theory used to be called the catastrophe theory, probably. And there is this, I think Arnold was one of the main, no? Sorry? Okay, I see.